Hello everyone, my name is Daryl Markowitz. I'm coming to you today from central Canada in Ontario, about 125 kilometers northwest of Toronto. This will be a fast overview of a paper that was prepared in collaboration with archaeologist Kevin Smith, and the experiments have been undertaken with the working assistance of Neil Peterson. We've had a shared interest in bloomery iron smelting furnaces going back some 20 years. Our focus has been to Northern Europe in the period from 800 to 1000 AD. This set of experiments will specifically reference a site in Iceland called Hals. In Iceland at the time of the settlement, there was considerable deposits of primary bog ore, a type used all through Scandinavia, and the island was still forested with birch to supply the required charcoal. Iceland's first settlers would have brought with them a furnace building tradition from Norway, which uses both clay and stone in the construction. Unfortunately, the geology of Iceland means there's very limited clay deposits available. On top of that, the clay that is available is often not able to withstand the 1200 degrees Celsius or more temperatures required in the furnaces. Archaeological excavations at Hals start in the late 1980s. Kevin Smith's work on the site focused specifically on the iron smelting components. Excavations would expose a number of furnace bases as well as suggestions of the actual superstructure of these furnaces. As well, there was uncovered a very large pile of leftover slag. All this suggested an industrial level site where iron was repeatedly made over several campaigns of production. Carbon-14 dating for the site places it at some time between 895 and 980. There were a number of slag bowls found in place in the base of the furnaces, which would have marked the last use of iron smelting on site. There was also very limited tap slag recovered. The furnace bases were broken away to the east-hand side, which suggests a bottom extraction of those final blooms. There were absolutely no fragments of ceramic terriers found on the site. In fact, there were only small fragments of clay recovered in the range of about 3 centimeter maximum. There's also very limited stone found around the bases of these last furnaces. The furnaces at Hals had an interior diameter of 30 to 35 centimeters. They were constructed of long cut strips of turf laid into cones to create the superstructure. This represents a very distinctive Icelandic style of building. The archaeology suggests that each one of these turf cones was surrounded by a timber-framed box, the space between the cone and the box filled with earth to create an upper working platform. One of the clay fragments shows a hole and is heavily vitrified. The positions of the stones suggest there was at least some use of stone to construct an arch or support for the terrier at the front. The relatively small amount of tap slag recovered, as well as the heavy slag blocks found, suggest that furnaces may have been constructed with space to allow slag to accumulate. Without either stone or clay to support the front wall of the furnace, extraction may have actually been undertaken from the flat platform at the top of each furnace. The exact details of the air supply system remain unknown, both in terms of the shape and size of the bellows and the type of terrier used and how air might have been inserted into the furnace. Over the period of 2007 to 2016, a total of 8 experiments would be undertaken specifically related to the Hals Icelandic series. An important consideration is the accumulated experience of this working team. Other projects were being worked on during this same 10-year period. There is no naturally occurring primary bog iron ore available in our central Ontario location. For this reason, the team had developed an analog, primarily Fe2O3, with flour added as a binder. Our standard furnace builds were in the same size range as those suggested from Hals, in the range of about 70 centimeters tall. However, we had been using freestanding, heavy clay cob walls. Most of our furnaces were slag tapping furnaces, as opposed to the slag-contained furnaces seen at Hals. One major area of experimentation was going to be with the air supply systems. Our standard was an insert to rear, usually a ceramic tube. The physical size of the furnaces seen at Hals, roughly 2 meters by 2 meters and standing about a meter tall, was certain to change the working dynamics around the furnace. The last and most significant element from Hals was learning to deal with the conical turf construction. The first grouping of 2 experiments were in the fall of 2007. Here we were working with furnaces built with stone on the front surface and using a blowhole method to insert the air. Both of these furnaces would use a section of steel pipe as the rear, set at the outside surface of the furnace. Both were constructed with a 20 centimeter lower area to contain the slag. Experiment number 2 would use a box-shaped furnace constructed of stone slabs, which resulted in its own problems. In both experiments, however, the slag was found to be contained in the lower slag room. There was found to be quite heavy erosion of the schist stone slabs used to construct the furnaces, starting at about 4 centimeters, but eroding down to 1 centimeter thick by the end of the smelt. There would be a gap inside the second grouping of experiments as the team was working on the Vinland project for Parks Canada. The primary focus of this group was outlying a 2 meter by 2 meter working area against the earthen bank in Wareham. Additionally, over this series of tests, we would gradually reduce the thickness of the clay walls. This group of 3 furnaces was all designed with a thin clay central plate that contained a circular blowhole. The rear was set proud of this blowhole to insert the air. Each of the furnaces had a 20 to 25 centimeter lower slag room. In each of the smelts in this set, it was found that the air did not properly penetrate to the interior of the furnace. This in turn caused the slag bowls to all form too high and too close to the front of the furnace. This would then result in there being the requirement for a lot of intervention in the control of slag. Eventually, each of these furnaces had to be tapped. The last group of 3 experiments would all use grass sod as the construction material. Experiment number 6 would actually have no clay used at all in the construction. Number 7, the liner thickness was reduced down to 3 centimeters. Both experiments 6 and 7 would use a standard ceramic rear, about 2 centimeters internal diameter, inserted 5 centimeters proud of the inner furnace wall. Both of these experiments would also use the slag room method to control slag. Both of these furnaces experienced considerable increase in slag production. This in turn resulted in damage to the furnaces during the extraction process. In fact, in experiment number 6, it was impossible to get the bloom out while the furnace was hot. Experiment number 8 in October 2016 would take place at Laurel, Ontario, about 50 kilometers south of our normal working area in Wareham. Richard Schweitzer would undertake a full-scale above-ground build of the turf construction inside a timber frame. This would be the first time Richard would fully manage an iron smelt, so in many ways should be considered experiential rather than experimental. Poor weather, limited time, and reduced experience would all combine to make the build process less efficient than normal. The final interior shape of the furnace was especially quite irregular. The drying process was also rushed, which caused considerable damage, which would affect the progress of the smelt. A heavy forged copper turret was used in this case, again with an interior diameter of 2 centimeters. The net result of all these aspects was a complete failure of the inner clay liner. This would fill the lower slag room area, not leaving a lot of room for accumulated slag. As a result, slag was continually tapped and modified through the progress of this smelt. Much was learned over this series of 8 experiments. What conclusions can be drawn? First and most importantly, the construction technique seen at Hals of a turf cone furnace inside of a timber box was proved to be viable. Iron was produced in every experiment. Our average bloom production was 20% for more. That being said, it remains obvious that still more experience is needed with this furnace type. Managing slag collection, especially in combination with certain air insertion types, remains a problem. It was found as the clay liners got thinner and thinner, it became more and more difficult to get the clay to physically remain in place against the fragmenting sod walls. It was certainly found that without a protective clay liner, the grass sods would collapse in the inner surface at the end of the smelt especially. Although all this may not cause a problem for a single smelt attempt, it was obvious that there was extensive damage to the furnaces, especially during the extraction phase. The difference in the underlying geology between Iceland and Ontario became apparent through this series. First off, the underlying bedrock in Ontario is granite, not basalt as it is in Iceland. The difference in subsoil between Wareham and Laurel indicated that the further change between subsoils in Ontario and Iceland may prove significant. There also remains the question of how similar our bog ore analog is to naturally occurring primary bog iron ore. It also became apparent that our experience and familiarity with clay-built short shaft furnaces would not directly map over to the use of Icelandic-style materials. Our review of our past work certainly reveals many questions remain to be answered. An attempt could be made to match the chemical components based on samples of Icelandic clay that we had analyzed. For future smelting tests, a complete above-ground build should be constructed. This furnace then should be used multiple times, both with some delay between tests, but also a series of smelts placed back to back, one bloom extracted, and then a second smelting attempt started immediately. An ongoing experimental series for this team has been an investigation of air supplied using a Norse-style bellows system. Ideally, this work then should be applied to the Hals build. The ideal conclusion to all this work would be to repeat this experimental series in Iceland itself using all locally available materials. Obviously, to undertake a project of this type, close partnerships would be required with working professionals in Iceland itself. Thank you for your attention today. I hope this presentation will lead you to read our full published paper. I need to specifically thank the other members of the Dark Ages Recreation Company who provided much willing labor over the last 20 years of experiments. If you're interested in viewing the full documentation of over 85 iron smelting experiments to date, I would invite you to take a look at the website.